Welcome back, ladies and gentlemen. We will now continue with the last part of the session. At this time, we will present some professors from the University of Illinois at Urbana-Champaign, and Professor David Cahill will be the chairperson. Ladies and gentlemen, please welcome Professor Cahill.
Thank you, and welcome to this, we'll call it the orange and blue session with the faculty from the University of Illinois. Yes, I'm David Cahill. I'm the professor in the Material Science Department at the University of Illinois and the head of one of these departments that Petros was referring to as one of the top departments. I think our colleague from MIT might have an argument with you over beer tonight, but we'll take the compliment. Thank you. The first speaker is Professor Angus Rocket, who's also from the Department of Material Science and Engineering at the University of Illinois. The fuller CV is on your sheet, but I just mention that Angus is under great demand around the world as a speaker about the material science and physics of copper indium diselenide-based photovoltaics, and also will soon be the president of a major professional society in America, the American Vacuum Society. So Angus will speak about materials and devices for driving photoelectrochemistry and hydrogen production.
Thank you, David. It's a pleasure to be here. I want to thank the organizers for inviting me. It's always wonderful to come to Japan. It's always wonderful to be involved in collaborative research with colleagues who are so expert in the field. I think you got a very good introduction earlier to artificial photosynthesis and some of the issues involved in making hydrogen. And I'm going to talk mostly about the energy input to that process, primarily through photovoltaics, and some of the work that's going on at the University of Illinois, potential collaborators who could participate in this program from there. So if you look at the stated goals of the program, they include development of high-efficiency materials for conversion processes without byproducts or waste of carbon dioxide. For that, you need electrochemical cells, as you've heard, and you need them driven by some sort of carbon-free energy source. For example, direct conversion of sunlight to electricity. And in addition, we want to look at ways of hydrogen production, photocatalysis, and that sort of thing. All of these processes require energy input in the form of electrons at high chemical potential. And so that's what a photovoltaic provides. And the people that I'll be mentioning today can also contribute in many other areas that you've heard about today. So it's a potential for a lot of collaboration. In terms of driving photocatalysis, an excellent way to provide electrons at high chemical potential is with a photovoltaic device. In particular, one might imagine a multi-junction photovoltaic. And you heard a little bit about that earlier with the two-stage optical absorption, the high-energy photon followed by a low-energy photon absorption. That's typical of a multi-junction photovoltaic where you have a blue absorbing solar cell that's transparent to red light. You put behind it a red absorbing solar cell, and then you put them in series. It adds the potential of the two cells, and so you get a higher potential out of the whole device. And the nice thing about a multi-junction cell is that you can tailor the energy gaps for very high efficiency. The record efficiency for a photovoltaic device is 40% efficient conversion of sunlight to electrical energy. And by tailoring the energy gaps and the way that you put those devices together, you can also tailor the net potential that you develop from the anode to the cathode of the multi-junction device. So you can adjust the way that you design the device in great detail for optimized performance with respect to an electrolyzing device. And then, of course, you need the electrolyzer, which will be discussed in the talk that follows mine. Photovoltaic devices provide sufficient output to split water directly. They're very high efficiency, as I just said. One of the things that you certainly have to worry about is protection of the device from photochemical corrosion in the material. And so one of the big issues will certainly be some sort of a barrier between the device and the electrochemical cell. There are a lot of technology options when you make a photovoltaic device. One can imagine single crystal epitaxial materials, crystals of semiconductors that make extraordinarily good solar cells. That's how the 40% efficient device was made. It is a little bit difficult to see how you can make those inexpensively by the square kilometer. And so you might turn to other options, and the two major options that people consider for inexpensive photovoltaic conversion of sunlight to electrical energy are, for example, organic photovoltaics, as you heard about in the earlier talk today by Professor Ishihara, or by inorganic materials, typically polycrystalline materials, and the least expensive materials for that are the chalcogenides. Currently cadmium telluride-based devices, and as you heard, I work on coperium diselenide, a similar sort of material. So these materials have tailorable band gaps. In particular, for example, the indium, gallium, aluminum nitride materials that you might imagine for single crystal devices have tailorable band gaps that cover the entire electromagnetic spectrum very effectively. This is a cadmium telluride cell from First Solar producing very inexpensive energy. So there's a lot of opportunities. The advantages of photovoltaics are becoming more obvious. And currently, in most environments in the world, photovoltaics can be competitive at the electric meter of the consumer for electric power production. It doesn't cover transportation, but at your electric meter for your utility, a photovoltaic device is probably competitive on your roof today at prevailing manufacturing costs. That doesn't mean you can go out and buy it. We can hope in a few years you probably will be able to go out and buy it at that competitive price, but today at least the manufacturing cost is different, okay, is very low. So what might we do? This is an example of, for example, a tandem structure device that you might imagine made of the chalcogenide materials. This is the current technology cadmium telluride device, coperium diselenide device. You could imagine stacking these together, perhaps altering the absorption coefficient of the cadmium telluride, which we know how to do, make a wider gap cell that would work better in the blue, and then gang those together as a tandem structure, which is easier said than done. And the total device would have an output that would be sufficient to drive an electrolyzer. You can also imagine doing this with organic photovoltaics. The organic photovoltaics community is developing very rapidly. This is a technology that one could imagine doing, for example, a printed technology, a printing process that could be done at very high rates, very low plant utilization costs, very large area depositions that could be done. It would be interesting to look at things, for example, like the nitrides as polycrystals and see if you could adjust the deposition conditions and the composition of the materials to passivate grain boundaries in that material system. They're much less susceptible to grain boundary behaviors than the less ionic arsenides are, and of course the covalent materials. Flexible devices are nice for many applications, and you can do this either by using organics, or you could consider, for example, a patterned microcell process such as one of my colleagues, John Rogers, uses, and I'll mention that in more detail in a minute. So just to consider a few examples of the work that's going on at Illinois, and perhaps you can see as I talk about these how they fit with the work that's going on here and how we can make a collaborative team out of the whole structure. This is a summary of Lane Martin's work in my department. He's working on oxide materials. These are ferroelectric materials. He's got a radically new concept, I think, for a photovoltaic device, where instead of relying on a heterojunction to separate an electron from a hole, he relies on a polarized ferroelectric material and takes advantage of that built-in polarization to separate the electron from the hole. And he can make devices that work, and he's exploring this concept. One can imagine then going on. These are relatively stable compounds being oxides for electrochemical corrosion, and so you could imagine very interesting new novel devices made out of these things. He's making photovoltaic materials as well from the copper oxides, which have been studied for a while, but they're coming back into fashion, and people are looking at new technologies based on the copper oxides. I think in particular, his work is very exciting, the combination of the copper oxide with things like titanium or iron oxide or some of the perovskites like the lanthanum strontium titanate. So these are exciting opportunities in an inorganic device. My colleague John Rogers, in the same department as I am, material science, is spending a lot of his effort on micro-patterning of solar cells. So he has developed technologies by which he can take a high-efficiency device, like a silicon device or a gallium arsenide device, that's normally very hard to process and requires a relatively thick substrate. And he's found ways of cleaving off thin layers of that material, picking it up, placing it somewhere else, and therefore cutting down greatly on the amount of material that's used, and in the end, making a flexible device. So this has a lot of applications, both in flexible photovoltaics, but also in much more effective utilization of things like gallium arsenide, and it has the potential to really revolutionize the manufacturability and the deployment of the arsenide-based solar cells. So this is the 40% efficient technology. Okay, so that's really exciting, something that we can use, again, to drive an electrochemical cell directly. My work is on fundamental materials science of solar cell materials. I do a variety of things. You can see I have the whole alphabet soup of surface and bulk characterization at my disposal. We do electrical measurements, and so I fit into the team here, both in terms of developing novel inorganic photovoltaic devices, but also in understanding and modeling them, modeling their performance. We're writing computer codes to do solar cell simulations that will take us on to novel technologies. There isn't a good model, for example, for organic photovoltaics at the moment. There isn't a good model for nanostructured photovoltaics at the moment, and the model that we're developing based on a two-dimensional grid system and a stochastic model can handle the very low carrier mobilities, can handle the time-critical series of events that you have in a nanostructured device, especially a multi-exciton or intermediate bandgap structure. And so we can provide both modeling and characterization along with inorganic materials and devices. The University of Illinois, as a collaborator in this project, has a very extensive range of characterization facilities, all the way from optical probes, SIMS instruments, surface scanning probes, and we would love to work with the groups here in terms of supplying material to us, characterizing it, feeding back to the groups here that are making devices. When you think about turning this into an artificial photosynthesis process, this is how I view it. You need, in order to make the completed device, you have to integrate a lot of parts together. So you could imagine saying, okay, we need to make a photovoltaic device. That could be an organic or inorganic-based device, or it could be a little of both. We need an electrochemical cell to go along with it. We need device modeling and simulation to figure out how the rest of the process worked. We need to characterize the materials that we make so we know why the device works or doesn't work. And then ultimately we can put it all together and make a completed device. So in terms of how I perceive a collaboration between Illinois and Kyushu, the work here involves particularly organic materials and devices. At Illinois, we're mostly working on inorganic materials and devices. There's electrochemistry at both organizations. There are characterization techniques at both organizations. Most of these are synergistic and complementary, so we can build a team together that I think really will advance the technology, drive this forward, and result in direct photoelectrochemical production of hydrogen. Finally, as a sort of a vision for the future, one of the comments that I like to make is the best hydrogen storage material I've ever run across is long-chain hydrocarbons. And we know, as you've heard from the talks earlier, we know that we can do electrochemical reduction of carbon dioxide. And in fact, you've seen evidence that we can put these two processes into a single electrochemical cell that yields syngas directly in the high-temperature steam reformer, and you can go directly through Fischer-Tropsch to a long-chain hydrocarbon. So we know that we've got all the pieces to go from sunlight or wind or any other form of energy to hydrocarbon hydrogen storage technologies, and we know how to use that in our vehicles today. So I think really what we're faced with is taking and optimizing all of these little process steps, not the least of which is gathering carbon dioxide from the atmosphere. But we can do all of these parts. We just need to do them better. And then we can store energy in the form of hydrocarbons, which we already know is a fabulous energy storage technology. So with that, I thank you for your attention. And if there's any questions, and if the chair provides time for questions, I'll take questions.
We do have time for a question. Rob?
Angus, this is off the wall question. With these organic photovoltaics, they offer cheap energy. Does anyone ever worry about how they'll degrade under UV radiation? I mean,
It's not just UV radiation. Organic photovoltaics are intrinsically unstable because you're breaking a bond. In the inorganic, you've got this distributed electron, distributed hole in the block states, and you can basically break a generic bond across the entire structure. In an organic, you essentially can figure out what bond you broke. And if you separate the electron from the hole, you wind up with unpaired electrons that travel around with the itinerant hole and electron. You carry around a dangling bond, a half-filled dangling bond as well. So yes, stability is a huge issue, but in current technology, 10,000-hour lifetimes have been obtained under the right encapsulation processes with the organics. And so I think it's a staggering improvement in performance. There's a lot of progress that's been made in organic photovoltaics. I think it's very exciting. What we really don't know is how the device operates on an atomic scale. What is the extremely low carrier transport doing for you? What's the best way to separate the electron from the hole? How can you reduce the exciton binding energy in the materials? There's a lot of work to be done, but the improvement in the organics is very impressive, in my opinion, and they really look like a very strong competitor in the long term. So they're well worth looking at.
Okay, thank you. Let's thank Angus again. And our next speaker is Professor Andy Gaworth. So Andy is a professor in the chemistry department at the University of Illinois and also the director of the School of Chemical Sciences. And Professor Gaworth is an expert in the interfacial chemistry and electrochemistry at electrochemical interfaces, and that's what we'll hear about today, fuel cell research at the University of Illinois.
Thank you, David, and thank you, Petros, for the invitation to come on out here. And I'd also like to thank the local committee for their very nice hospitality, and all of you for sticking around to late into the afternoon to hear me talk. Now, what I'm going to talk to you about today is work that we're doing at the University of Illinois having to do with fuel cells. And here, I'm very fortunate that Professor Sasaki has already introduced you to this concept. But I think you'll see that there are a number of different kinds of perspectives that you can have on fuel cell research. And mine is perhaps a little bit more fundamental, and his is perhaps a little bit more device-driven. So, what is a fuel cell? Many of you know what this is already, and, but I just thought I would sort of review it for you because there's an important point to make. So basically what you're going to do is you're going to oxidize a fuel of some type at what we call the anode right here. And the fuel that people typically are talking about these days is hydrogen, in part because it's easy, and in part because doing anything else with, say, methanol or ethanol, or as somebody once called me up and said, what about kerosene, is difficult. So we're going to oxidize hydrogen, and we're going to make protons and electrons. The electrons are going to go and turn the wheels on the car or the light on the top of the car or something like that. And the protons in this polymer electrolyte membrane example right here are going to go across the electrolyte or separator right here until they go to the cathode. And at the cathode, more chemistry is going to occur. Here what's going to happen is those electrons are going to come back around. We have the protons right here, and then we need to reduce something. We oxidize on this side, so we need to reduce on this side. And the thing that everybody suggests is that we reduce is oxygen. So we're going to take oxygen right here and 2 electrons per half oxygen, or 4 electrons, to make water. So on one side, we oxidize hydrogen to make protons and electrons, and the other side, we use those electrons to reduce oxygen to water. Okay, so why use a fuel cell? Well, it's a very efficient electrochemical device. We can turn a fuel directly into electricity without prior combustion and with no moving parts. And as had been mentioned several times today already, this process is the opposite of electrolysis, and we're going to run on hydrogen and oxygen. Okay, great. Now, Professor I²CNER pointed out to us that, let me just say that there are a number of different types of fuel cell types right here. We have an alkaline fuel cell right here. This was the, what was in the Apollo 13 that blew up, if you might remember. All right. The ones that we're going to work on are either these PEM fuel cells, which work on hydrogen and are CO2 tolerant, all right, or direct methanol fuel cells, all right, which are a little less popular these days. And then we also have heard some talks today about solid oxide fuel cells. But there are other types, phosphoric acid fuel cells and molten carbonate fuel cells, and these have sort of fallen out of favor these days, although they could come back. And the areas of application for these, again, as we saw, range from things like portable electronic equipment to mobile and residential generation to cars and boats, and this is where PEM fuel cells in particular are being talked about, and to distributed power generation, and this is perhaps where a solid oxide fuel cell would be most or best used. Okay? Now, the main advantage of the fuel cell, and this is the very important point, the main advantage of the fuel cell is the high thermodynamic efficiency. I can take hydrogen and oxygen, and I hope you can too, and figure out a way of getting power out of it by simply combining them and flicking a lighter, and presto, you get combustion. But then, of course, you're Carnot cycle limited, and that Carnot cycle limitation, hydrogen is a low temperature burning material, and so that Carnot cycle limitation basically means that you're not thermodynamically very efficient. In contrast, this is a chart I took out of Physics Today. It was an article about 10 years ago. In contrast, we can have very high thermodynamic efficiencies with all of these different fuels. So you can see right here, we can, after you include the entropic term, we can have thermodynamic efficiencies up to in the mid-80s for hydrogen, and ranging to over 100% because of the entropic term. All right, we're not creating energy out of nothing. So compared to an internal combustion engine, we have very high efficiencies, the best known way to convert chemical energy of fuel into electricity. All right, so a typical Otto cycle engine, we're talking about thermodynamic efficiencies in the mid-20s, and the best diesel to date only attains about 40% of that. All right, so it's actually fairly low. Compared to a battery, we have significantly greater energy density, and it's much faster to recharge or refill. So far, so good. Now, as Professor I²CNER pointed out today, fuel cells are not a new concept. Grove was the first one to introduce this concept, and he was working in 1840. That was a long time ago. So why is it now that we are just now talking about putting fuel cells into the transportation infrastructure? Grove, 1840. Ostwald was a big proponent of this in the 1890s. All right? And so why has it taken so long to do this properly? And part of the reason, not the whole reason, but part of the reason is shown on this chart here. So this is a chart of cell voltage versus current out of a real hydrogen air fuel cell. Now, the cell voltage right here is what we call the difference between the two half cells. One of the half cells is, as I showed you, the hydrogen ion part. And that's running at, let's just call that 0. All right? The other part, when we make that hydrogen ion at 0, the other part is the oxygen-water couple, and that's up at around 1.2 volts or so. It's a little lower. We have less oxygen in the air, so it's a little bit lower right here. What you can see is that even before you start passing any current at all, you don't develop that 1.2 volts. You actually develop about 300 millivolts less. And then as you start passing current, and people think that realistic amounts of current are talking about 1.5 amps per square centimeter of electrode area, you can see that the cell voltage drops considerably till it's less than half of what the thermodynamic value is. Now we can analyze what the cause of this drop is, and it turns out something like 2/3 of that drop just comes from the slow kinetics of the oxygen reduction reaction. Okay? So in other words, cleaving that oxygen-oxygen bond, doing that chemistry is very difficult in a PEM fuel cell. I'm not talking about a solid oxide fuel cell, where of course there's a different type of chemistry going on entirely. All right? Now, we can look at that drop right here, and it's very easy to convert this drop in cell voltage to a thermodynamic efficiency. And when we do, what we discover is that the thermodynamic efficiency in this best case scenario works out to be on the order of about 45% or so. And so that's not nearly what we think what we can get thermodynamically out of a fuel cell. It's actually substantially less. Now, as good chemists, we know that if the rate of a reaction is slow, if the number of turnovers per sites per second is slow, all we need to do is add more sites. In this case, unfortunately, those sites are made from platinum or one of its alloys. And so maybe you've heard things like there's going to be $5,000 worth of platinum on the vehicle or $10,000 worth of platinum on the vehicle. I think you can choose any number you want because you will be correct as the price of platinum increases without bound. But one of the problems is that the platinum loading, particularly for this oxygen reduction reaction, is very high. And so we want to get rid of that. Even worse, the platinum shows some degradation processes. It migrates across the fuel cell, depolarizing the cell. It's a total disaster area. Okay, so we have too much platinum. It doesn't really work with any fuel but hydrogen, and the thermodynamic efficiency is not what is advertised. Okay, so what we want to do is we want to step back. We want to understand what the mechanism of this oxygen reduction reaction is. And then what we want to do is use this mechanistic understanding to develop a new catalyst that will solve all of our problems and move us on to greater glory. Okay, so let's see. What do we know about the mechanism of the oxygen reduction reaction? Well, it turns out not too much. This is work by a very smart American electrochemist named Ernie Jaeger some years ago. And Jaeger, who did not use molecular-based tools, was smart enough to know what he didn't know. But he proposed perhaps there are 2 platinum sites involved. He couldn't tell whether it was end-on or side-on, what the intermediates were. And let's just say that this was a good guess. So don't copy this down. Please don't. All right. Now, so this leads to a whole series of questions. What's the mechanism of the oxygen reduction reaction on platinum and with other catalysts? What are the intermediates in these reactions? How can we replace platinum with less expensive materials at both the anode and the cathode? How can we reduce the overpotential, which is telling you what's killing you thermodynamically? How can we oxidize other hydrocarbons? So I think Angus pointed out that storing hydrogen in a hydrocarbon is actually much more efficient than storing it in a hydrogen tank, all right? And reduce CO2. And how can we efficiently electrolyze water to make hydrogen? So all of these things are what we need to do in order to make this work properly. And so I'm going to very quickly just go through some of the things that we've done in this way. Okay. So we've done a lot of mechanistic work. We do vibrational spectroscopy. We do calculations. And I will say that all the work we do show the presence of surface hydroxides, which we believe come from this cleavage at the peroxide level. All right, don't take notes because we've done X-ray scattering experiments to look at platinum-platinum distances as a function of oxygen presence and of potential. We can do TEM to look at real catalysts on surfaces. These are individual copper atoms on a carbon electrode surface. And from this, we can come up with a series of mechanistic ideas. And the outcome from all of these experiments and calculation is to show that at least 2 metal atoms are required to cleave the oxygen-oxygen bond. So that's one thing that we know we want to do. Okay, so with this idea, how can we make new oxygen reduction reaction catalysts? Several ways. One way is by making metal surfaces or clusters or using alloys. The so-called D-band model, which is a consequence of something called the principle of Sabatier, important in catalysis, is often used. Platinum nickel is the best so far. We can heat treat carbons. All right, there are a lot of work this way. Dodelay is perhaps the most known for this. You can pyrolyze a carbon at 850 C and actually get something that works fairly well if you include a metal. You can make other polymers with metals. Cobalt polypyrrole is the best exemplar right here. You can do combinatorics with all of these. We won't talk about that. You can work in the basic electrochemical environment, forbidden here on Earth because of the formation of carbonates in the electrolyte, which are lower your conductivity. But things like the zinc air battery or gold 100 in base work fairly well. We don't fully understand why. And finally, we can look to what nature tells us. And it's this point that I want to emphasize here. So it turns out nature has solved the oxygen reduction reaction problem. All right? Nature does this. In fact, right out there, right on the ground out there, there's an enzyme called lacase, which is right away now reducing oxygen at near thermodynamic potentials, and it uses that energy to oxidize various things. All right? What it features is a 3-copper active site right here, and a series of intermediates that are not dissimilar from what I very quickly glanced over before. The interesting thing about this is that many people have shown is that this catalytic material is substantially better than platinum. And so all we have to do is figure out how nature did it, and then we are better than platinum, and we solve this problem. We've done some of that. We have a material based on this 3,5-diamino 1,2,4-triazole right here, which forms a binuclear copper site. We've shown that this catalyst is is the best catalyst for copper at intermediate and higher pHs right here. And that's been we've been spending a lot of time working on that. At the same time, my colleague Tom Rackfus has been working on the anode reaction. Recall that's where you're oxidizing hydrogen. And he has a biomimetic catalyst based on these iron-nickel hydrogenases right here. So here is his catalyst, and he's shown that he can get a very efficient oxidation of hydrogen with only a small overpotential. In fact, the best overpotential for hydrogen on this material. So now what we can do is we can test these materials using a microfluidic platform developed by my colleague Paul Kennis. All right, he can do both the hydrogen side and the oxygen side simultaneously with a reference electrode. And he has tested our diaminotriazole catalyst. And what he has shown is that in base, this catalyst is about 5 times better or 5 times higher mass activity than platinum carbon material right here, and better than the more traditional silver carbon material that was used in, for example, the alkaline fuel cell in the Apollo situation. Okay. So with this one example, I can give you some ideas of the kinds of synergistic collaborations that we might engage in between Kyushu University here and the University of Illinois. So here we've seen talks about novel supports, about solid oxide fuel cell materials, about oxides, about separators, about ionic conductors. And at Illinois, I think we're fairly good in catalyst development and characterization, in oxides, in electrolyzers, and in work looking at oxidation of hydrocarbons. And taken together, I think what we can do is make an advanced catalyst, advanced fuel cells, and advanced electrolyzers. And I'd like to just close with the final thought, and that is this is a great time to be involved in electrochemical work because it is charge transfer at interfaces. I think that's the major theme that we've seen in all of this work right here. Charge transfer at interfaces is what's going to make us have a better energy future. Thank you very much.
We have time for a question if the answer is short. Go ahead.
So at last, why platinum needs such large overpotential for the reduction of oxygen?
Right. So this is what people believe is it's because of the formation of surface hydroxides at these higher potentials. And once you form this native hydroxide, the catalyst is dead. The whole idea behind these alloy materials is to destabilize the surface hydroxide, make it harder for the surface hydroxide to bind to that surface. And so the best catalyst, I said, is a shell of platinum on top of a nickel-rich second layer, and then more platinum down below that. Okay, destabilize the surface hydroxide.
Okay, so you mean the catalytic activity depends on the potential? You mean the catalytic activity of the platinum changes? Okay.
Oh, absolutely. That's all. No, absolutely. Sure.
Okay. Okay. I understand.
Perfect.
Thank you.
Thank you. Okay, our final speaker in the session is Professor Jim Stubbins from the Department of Nuclear, Plasma, and Radiological Engineering. Professor Stubbins is also the head of the department. I believe he's the longest serving head in the College of Engineering. At least if you integrate over time, over his career, certainly this is true. And Professor Stubbins is an expert in materials under used in the nuclear industry. So if you think hydrogen is bad for metals, try exposing it to high temperatures and radiation environments and corrosive environments all at the same time. And I think that's some of the things we'll hear about here today. Nuclear production of hydrogen's approaches, challenges, and rewards.
Yes, thank you, David. And thank you to the organizers. I also really appreciate people being here, and thank you for the invitation to talk. I think today what I'll talk about is less about materials issues and back a little bit about where we stand with the production issues. And part of this, I think, is motivated by the very aggressive goals that this particular center has, particularly looking at having a major impact within the next 4 or 5 years. And I think many of the things that we've heard about today are things that will have an impact, but likely not in the next 4 or 5 years. And I think also one of the issues that we're always looking at is the mix of solutions. I would agree with Dr. Finley earlier that there's not one solution to this, there are many solutions. And we have to keep those in mind. And so what I thought I'd talk about today are some of the issues involved in using nuclear power to do these kinds of things. And I start with this figure. This is a figure that comes from the Department of Energy in the US. And in particular, what it shows is energy sources on one side and where they're used on the other side. And particularly, you'll notice that, this is a nicely done diagram because you can see the size of these is related to the amount they're used to make up the full energy picture in the U.S. Not so unlike here in Japan. We heard from Dr. Finley earlier, this adds up to about 85% in Japan, also in the U.S. So fossil fuels account for probably 85% of the total energy usage in the U.S. Renewables and nuclear add up to the other about 15% of what's there. And one thing you'll notice is that apart from the fossil fuel applications, primarily nuclear energy is used 100% for electricity generation. It has had no or very little impact here. Renewables also, a large fraction of them traditionally have been in electricity production. This is hydroelectric power production, though this has changed somewhat with biofuels and other kinds of things recently. But the issue for us for here is what to do about these things. And I think nuclear and renewables, we've heard a lot about renewables today, will play a role. And so the issue really is this: how do we get nuclear or these things down here to have some impact on the transportation industry? And you've heard two ways. One is to make hydrogen, which will run fuel cells, which will run autos. The other way, of course, is electric vehicles or electric-assisted vehicles, where electricity is used to power vehicles that would take up part of this major reliance on petroleum to support the power industry. And so I think this is the goal of nuclear. It's the goal also of several forms of renewables, particularly hydroelectricity and other things. And I think nuclear has a place to play in this area right now. So the very near-term things that nuclear can do, we heard about, are providing electricity for doing ambient or lower temperature electrolysis. Medium term, we can go to higher temperature electrolysis, which improves efficiency, as we heard earlier. And then longer term, though this is ongoing now, there are a number of thermochemical processes, one in particular, which are being developed to do much higher efficiency conversion of water or splitting of water into hydrogen and oxygen. And there are some very long-term goals, which I'll remind you of. These are concepts that were here 10 years ago, at least at the end. And so this gives you an idea about where the primary sources are. Again, this is like the first chart. You'll notice that, again, these are the primary sources in the U.S. The first primary source in terms of quads produced that's non-fossil is nuclear. And this is a very large fraction. If you add all of these things together, this accounts for roughly 70% of the U.S. energy production. So this is the indigenous energy portfolio the U.S. has. The other 30% is imported, and the other 30% basically is equivalent to the transportation costs that we have for energy. So a third, 30%, or 25 to 30% of the energy that's used in the U.S. is for transportation. If you look at the import of oil, that's all of the oil we import. If we had no transportation sector, we would have very little need to import oil. Or alternately, all of the imported oil supports the transportation sector. If you look at some issues about where the carbon is produced and where the major footprints are, this is a very recent report that was done by CRI EPI here in Japan. The date of the report is 2009. And you can see the fuel consumption, carbon emission, as well as the life cycle of building the infrastructure involved with those energy systems. And you notice coal, oil, liquefied natural gas, these things all the way down to nuclear here, geothermal, and hydro are the least energy or carbon intensive of any of the energies. Of course, this is true in the nuclear case because it's a lot of energy for a little bit of carbon footprint in the construction process. So this I think, makes a major case that nuclear should be a big part of what one can do. Another issue with nuclear is very good at doing at base load energy production, electricity production. So here you see a schematic chart. This again is taken from the electricity review, Japan electricity review from just last year. And you notice coal and nuclear, particularly hydroelectricity, are very good for base loading. People often do peak loading by other kinds of more easily burnable hydrocarbons, particularly in the U.S. natural gas. And this is an indication of prices of electricity on a hot day in August in the U.S. and on a cold day just 1 month ago. So the first of this year. This is not 2001, it should be 2011. And you'll notice that the peak load in the summer is very high, so there's excess capacity in the winter when the loads aren't nearly as high. This is, remember, Chicago. Chicago is 80% nuclear electric. And you'll notice also that on this day a month ago that if you got up early enough or stayed up late enough, the company would pay you to take electricity from them. There are some negative prices here. And this is not uncommon in this scenario because when you have mainly baseload power, you have to get rid of it. It's more costly to turn things up and down than it is to just give the energy away, which I think makes a good argument for using this differential capacity here as well as this late night, early morning, low-priced electricity cost to manufacture hydrogen. This is a comparison of 2008 and projections for 2013, 2018 for Japan's electric production, and you can see the nuclear fraction is proposed to increase significantly from around 26% to maybe 40%. I've replotted these numbers here, Japan, so these numbers from Japan 2018, Illinois in actually 2009, so last year, and you see that even Illinois is half nuclear electric. And this also, I think, makes a strong case for a major support of the hydrogen production using, at least in the near term, electrolysis from nuclear energy. And so the next step, and this is a step which is evolving both in Japan and in the US, is to look at a much higher temperature system where you could start to do thermochemical processing in order to produce hydrogen at a much more efficient way. And so this is a conceptual picture of what is now called in the US the next generation nuclear plant. It's a very high temperature gas-cooled reactor which is connected to an electric supply system as well as actually in this case a couple thermochemical supply systems. This is an existing reactor in Japan. The high temperature experimental test reactor, HTTR is the acronym, and it is currently in the process of building a thermochemical processing plant for hydrogen production. This particular reactor has reached an outlet temperature of 950 C 6 or 7 years ago. So this has been operating at a high enough temperature to make very high temperature electrolysis or to drive thermochemical reactions possible, and this has already been done. The sulfur iodide, the next slide you'll see, the iodine sulfur plant is this one which is being built. So you see IS here, even for those who can't read the rest of the script. And this is a system that should be operational by 2015. So also on the timeline here, but as a demonstration. And so this is the proposed, there are many cycles for producing hydrogen. This is the so-called iodine sulfur cycle, which is the one that's being pursued both in the US and here. High temperature nuclear heat up to 900 C, and a low end at 400 or 500 C, maybe even lower than this. And there are two cycles which produce hydrogen at the low end and oxygen at the high end. Okay? And this would be an efficient way. The efficiency, the calculations at least of the efficiency of the system could, for hydrogen production, could exceed 50 or 60%. So thermal energy to hydrogen production. The problem with this system, of course, is that the cycle requires very high temperatures. I'll say one word or a couple words about materials in a minute. Corrosive atmospheres and all kinds of other things that are very difficult for materials to withstand. Not so different, but in a different temperature range and a different atmosphere than some of the lower temperature issues with hydrogen and materials. And so materials development is a big issue, and also this particular cycle on a large scale hasn't been proven yet. And so this has to be done. But as I said, this is under development now and will be deployed by 2015 at HTTR here in Japan. So there are lots of materials issues, and I've done one slide as a snapshot of all of these. This is a typical heat exchanger in this system, which is the primary materials issue for very high temperature issues. And so there are lots of strength problems. This shows a strength. This actually is yield strength versus temperature. And you can see at high temperature, maybe you can't see, by the time you get up to 900 C, the temperatures are a fraction of what they are even at moderate temperatures up to 600 C. There are a lot of issues with corrosion in these materials. There are a lot of issues with materials fabrication and internal degradation under loading conditions. We've developed some techniques to look at these bulk changes in properties at very high temperatures, which is shown here using synchrotron radiation sources, so X-rays, very high energy X-rays, which can penetrate and tell us something about the materials deformation characteristics of the materials. I have to say, I should back up and say that before I started at the University of Illinois, I worked for General Electric, and basically these are the same problems, this is now 30 years ago, that we were working on in General Electric in those days. Very high temperature gas-cooled reactor, primarily in the US for very efficient electricity production. Japan's program at the time was also a hydrogen production program, so we're 30 years on and we're still trying to do that. Not for transportation applications, but for steelmaking applications. This was for reducing iron ore, which was seen as a major energy and cost motivator for the steel industry in Japan at the time. The third partner was Germany. Germany wanted to gasify its brown coal or liquefy its brown coal for transportation applications. And all of those programs, apart from a continuation that occurred here in Japan, collapsed in the early 1980s. Japan was the one outlier that actually had the I guess, foresight to continue with the program and build the HTTR. The German reactor right now is sitting in China near Beijing, so it tells you also something about how things have transformed. So anyway, materials is a major issue. And I'll end on this. This is a concept that many of you may have seen. This is a concept 10 years ago, but we at Illinois actually have held a couple workshops in conjunction with EPRI, with EPRI, the Electric Power Research Institute in the US. And this is a so-called supergrid concept, actually developed or proposed by Chauncey Starr, who was the founding leader of the Electric Power Research Institute in the US. And the concept is both a superconductor surrounded by a hydrogen transport, liquid hydrogen transport system on a major grid where you could produce hydrogen with a number of techniques, including very high temperature gas-cooled reactors, and pump both the hydrogen, liquefied hydrogen and electricity very large distances for both electricity and for very low loss electricity supply and for supply of hydrogen on a national basis. This is certainly a long-range thing, but it does show the synergism between particularly nuclear energy and the electric generation part of nuclear energy and the potential for hydrogen production with nuclear energy. So in summary, I think the major issue with nuclear is that it has some very near-term applications. It can already be important for producing hydrogen with very low carbon footprint. In the longer term, there are much higher efficiency applications that can be developed and are being developed. And in the very long term, there are these potentials for high conductivity and transport issues related to liquid hydrogen that people haven't started to address yet. In the meantime, there are a number of major R&D issues that need to be addressed. So I'll stop there.
Thank you.
Thank you.
A big thank you to Professor Cahill and all of the speakers. Our last speaker today is Professor Nobuhide Kasagi of the University of Tokyo, who is a program officer of the World Premier International Research Center Initiative, or the WPI. Ladies and gentlemen, please join us in welcoming Professor Kasagi.
Thank you. Director Sophonis, Director Murakami, distinguished professors, ladies and gentlemen. My name is Nobuhide Kasagi. I'm from the University of Tokyo. It's my great pleasure and honor to serve as a program officer for this particular WPA program, International Institute for Carbon Neutral Energy Research at Kyushu University. It is also my great pleasure to be here today and have listened to a very interesting talks throughout the symposium. Let me first congratulate all of you for participating in this important program on a good start today. I have already known from the written documents that this I²CNER has a wide range of very ambitious research targets, as well as a unique organizational structure involving world-leading scientists. But today, I have been even more impressed by the great enthusiasm Director Sophonis and other speakers have indicated. The drastically increased consumption of natural resources in the last century now threatens our planet and the livelihood of future generations. Key policy making for sustainable development hinges on optimal management of natural resources for the societal needs of energy, economy, and the environment, as you know well. To help promoting such strategies, we should face significant challenges to create relevant scientific knowledge, as well as develop new methodologies to enrich our life with the least impact on the environment. The current government's basic policy established last June, which is called New Growth Strategy, advocates two innovations. That is, green innovation and life innovation. Many countries are now pursuing the so-called green growth. Therefore, I like to emphasize that you should be aware of this nation's growing hope toward a new science and technology leading to a sustainable society. In this sense, a carbon-neutral society should be the unavoidable direction for both present and future generations. And every sector, including the scientific community, should make utmost effort. I'm sure the hydrogen utilization as well as the CCS technology is certainly among primary technological goals. And I have enjoyed the talks on unique and interesting research programs toward the future hydrogen and CCS technologies during this kickoff symposium today. If I may say something about what I'd like to see in this WPI effort, it would be a holistic scenario toward a low-carbon society for some trial cases, say Japan and the US, in the years of 2030 or 2050. You should, on the basis of scientific evidence, draw a future perspective, put every major technology on the entire roadmap, and always try to review the relative significance of the technologies you are pursuing. It is mandatory to resolve energy, economical, and environmental issues in a good balance. Therefore, in addition to deepening and advancing the knowledge on hydrogen and the CCS technologies, I hope you will continue to review and update the scenario itself during this WPI program. I also hope that this WPI will play a key role of networking other research bases already existing at universities, national laboratories, and industries in Japan, as well as over the world, and establish a strategic plan to collaborate with scientists of diverse disciplines. There are already a unique ongoing research activities, and they are working intensively, for example, on solar energy batteries, fuel cells, electric and hybrid cars, and bioresources. I believe that scientists and researchers need to work together toward a shared goal while playing their own roles. And that is perhaps what the society and the taxpayers eagerly wish. Once again, I'd like to congratulate all of you on this exciting start of the WPI program. And I will look forward to seeing major breakthroughs in your international challenge. Thank you.
This brings us to the conclusion of the conference. Thank you all very much for coming out to Kyushu University to attend the I²CNER's kickoff symposium today.